Hi friends, welcome to the lecture of linear algebra. In last lecture, we have seen what is a diagonalizable operator and some results on this diagonalizable operator. That is, geometric multiplicity of each eigenvalue will be equal to its algebraic multiplicity. Then the corresponding linear operator will be a diagonalizable operator. Okay. Now we have to see one theorem. Let T be a linear operator on a finite dimensional vector space V and C1, C2, up to so on Ck be distinct characteristic values of B. Distinct characteristic values of linear operator T. Okay, and let Wi be the characteristic spaces associated with the characteristic values Ci of linear operator T. Okay, now if W equal to W1 plus W2 plus up to so on plus WK, then dimension of this W is nothing but dimension of W is equal to dimension of W1 plus dimension of W2 plus up to so on plus dimension of W. Okay, and if curly Bi is an ordered basis for these characteristic spaces Wi, then curly B, which is a collection of these B1, B2 up to so on Bk, is an ordered basis of this W. Okay, first given that T be a linear operator which is defined on a finite dimensional vector space V over the field F and C1 C2 up to so on Ck, Bk distinct characteristic values of a linear operator T and Wi whenever I running from 1 to k be the characteristic spaces, that is eigenspaces associated with the characteristic values when Ci of linear operator T. And if we have given that W is nothing but W1 plus W2 plus up to so on Wk, that is it is a addition of these characteristic spaces associated with its corresponding characteristic values. Then we have to prove that dimension of W is nothing but dimension of W1 plus dimension of W2 plus up to so on dimension of Wk. And if suppose curly Bi is an ordered basis for this each Wi, that is characteristic spaces, then we have to prove that the collection of that basis, which is nothing but curly B, which includes these k characteristic spaces, that is basis of these k characteristic spaces curly B1, curly B2 up to so on curly Bk. Then we have to prove that this set is a basis for this W, that is basis. If we have to prove that this curly B is a basis for W, then we have to prove that this curly B is a linearly independent set and it spans the our space W. Okay, now if suppose if this curly B is a basis, then it is a linearly independent and it spans W. Therefore, dimension of this curly B is nothing but dimension of each of these bases. And if suppose this one is a linearly independent set, then dimension of this curly B is nothing but that is dimension of curly B is nothing but the dimension of, that is number of linearly independent elements in this curly B are nothing but the dimension of subspace W. So dimension of W is nothing but number of elements in B1 plus number of elements in B2 up to so on number of elements in Bk. Addition of these elements is nothing but that is number of elements in each basis whose sum is nothing but the dimension of that W. So here first we have to prove that this curly B is a basis for this W. Okay. Now given that prove given that T be a linear operator on finite dimensional vector space V over the field F and C1, C2, up to so on Ck be distinct characteristic values of T. Be distinct characteristic values of T, that is eigenvalues of linear operator T, and Wi be the characteristic space associated with each characteristic value Ci of linear operator T, and also W is nothing but the W1 plus W2 plus up to so on Wk, and we have to prove that dimension of W is nothing but dimension of W1 plus dimension of W up to so on dimension of this W. Okay, now we know that any characteristic vector can be associated with at most one characteristic value of a linear operator T. That is, we know that any vector alpha belonging to V cannot correspond to more than one characteristic value. Okay. One characteristic value of linear operator T. Okay, as each vector is associated with at most one characteristic value, then these Wi's are the characteristic spaces associated with each characteristic value Ci of T. But here we know that alpha belonging to V be any vector, then it cannot be corresponded to more than one characteristic value of T. Then this W1, W2 up to so on Wk must be distinct, since the characteristic vector characteristic spaces associated with the different eigenvalues must be distinct, which implies W1, W2 up to so on Wk must be distinct. Since characteristic spaces are nothing but the collection of characteristic vectors, and each Wi contains distinct characteristic vectors. Therefore, this W1, W2 up to so on Wk must be distinct. As W1, W2 up to so on Wk must be distinct, which implies Wi intersection Wj is equal to 0 subspace only for each I not equal to j. Okay. Now we have to prove that the curly B is an ordered basis for W. Okay. To prove that curly B is basis for W. For that, we have to prove that if alpha 1 plus alpha 2 plus up to so on plus alpha k is equal to 0 for each alpha I belonging to W, which implies alpha I must be equal to 0 for all alpha I belonging to W, and I will become 1 to k. Okay? That is, if the sum will be equal to 0, then this alpha I must be equal to 0. First we have to prove this. Let us consider alpha 1 plus alpha 2 plus up to so on plus alpha k equal to 0 whenever each alpha I is belonging to Wi. Okay, each alpha I is belonging to Wi. Okay, now let fx be any polynomial over the field F. Okay, and we know that we have proved one result. If T is linear operator on a vector space V and C be any characteristic value of linear operator T and Fx be any polynomial over the field F, then F of T of alpha is nothing but Fc of alpha. Okay, therefore let f of t be linear operator on V. Let us take this one as equation 1. Now operate f of t on equation 1. We get operate f of t on 1. We get, okay, therefore f of t of alpha 1 plus f of t of alpha 2 plus up to so on f of t of alpha k is equal to f of t of this 0. Okay, now from previous that theorem, that is if T be linear operator on a vector space V and C be any characteristic value of a linear operator T, then and if it be any polynomial over the field F, then f of t of alpha will be it is nothing but f of c of alpha. Therefore, from this theorem, which is nothing but fc of alpha 1 plus fc of alpha 2 plus up to so on fc of alpha k, and f t of 0 is nothing but actually it is a linear operator, and t of 0 is nothing but 0, which is nothing but 0. Okay, now we have to choose the linear functionals f1 comma f2 up to so on fk such that fi of cj equal to delta ij, that is by conical delta notation, which is equal to 0 whenever I is not equal to j and equal to 1 whenever I equal to j. Now we have to operate these linear functionals f1 f2 up to so on fk on equation 1. Then we get first operate f1. Sorry, that is f1. Then operate f1 of t on 1. We get on 1. We get from equation 2. Let us take this one as equation 2. Then from equation 1, when we operate f of t on alpha this equation, then we get fc of alpha 1 plus fc of alpha 2 up to so on fc of alpha k will be equal to 0. Whenever we operate f1 of t, then we get f1 of c1 alpha 1 plus f1 of c2 alpha 2 plus up to so on f1 of ck alpha k. Here f1 of c1 alpha. This is for particular f and linear operator t. But from this equation 2, we get when we operate f1 of t, then we get f1 of c1 of alpha 1 plus f1 of c2 of alpha 2 plus up to so on plus f1 of ck of alpha k is equal to 0. But from equation 3, fi of cj will be equal to delta ij whenever equal to 0 whenever I is not equal to 0 and equal to 1 whenever I will be equal to 0. Therefore here 1 is equal to 1. Therefore this value is 1 into alpha 1 plus 1 is not equal to 2, then its value is 0 into alpha 2 plus up to so on 1 is not equal to k, then it is 0 into alpha k, which is equal to 0, which implies alpha 1 equal to 0. Therefore, when we operate f1, then we get alpha 1 is equal to 0. Similarly, operating f2t, f3t up to so on fkt, then we get alpha 2 equal to 0, alpha 3 will be equal to 0, and up to so on alpha k is equal to 0. Therefore, here if alpha 1 plus alpha 2 plus up to so on plus alpha k is equal to 0, which implies alpha I will be equal to 0 whenever each I will come 1 to k. That is, and each alpha I is belonging to this W. I am nothing but alpha I belonging to this W. This W is nothing but W1 plus W2 plus up to so on W k. So here we have proved that the sum alpha 1 plus alpha 2 plus up to so on alpha k will be equal to 0. Then each alpha I will be equal to 0 for each I running from 1 to k. Now we have to prove that this curly b is a basis for w. For that, first we have to prove that curly b is linearly independent. Okay. Now if we consider a linear combination of elements of curly b and equate it to 0, equate it to 0, then the sum has the form, has the form that is beta 1 plus beta 2 plus up to so on plus beta k will be equal to 0 whenever each beta I is belonging to our curly here, or it is a subset of each wi. And if beta 1 plus beta 2 up to so on beta k will be equal to 0 whenever beta I belonging to curly bi, that is beta I belonging to wi. Then from this equation 4, if alpha 1 plus up to so on alpha k will be equal to 0, then alpha I must be equal to 0 for each alpha I belonging to wi. As here each beta I belonging to wi, then this sum must be equal to 0, which implies each beta I is equal to 0 for all I from 1 to k. Actually, this sum is nothing but this beta 1 is belonging to w1, beta 2 belonging to w2, up to so on beta k belonging to wk, where this each curly bi is a basis for this wi, is as curly bi is a basis for wi and beta I is belonging to wi, then any element of this wi can be expressed as a linear combination of its corresponding basis, and for wi its basis is curly bi. Then this b1 is nothing but the linear combination of elements of its basis curly b1. Beta 2 is nothing but the linear combination of elements of its basis curly b2, up to so on this beta k is nothing but the linear combination of elements of its basis curly bk. Okay, so the above sum is nothing but the linear combination of elements of beta I. Okay, and we know that each beta I is a basis for wi, and each beta 1 is a express, therefore as then any alpha belonging to this beta I can be expressed as a linear combination of this beta I, and each bi is a basis for wi, then the scalar in this linear combination must be equal to 0. Therefore the scalar in this linear combination must be 0, which is true for each beta I, each bi, since each bi is a basis for wi, therefore each scalar in each bi must be equal to 0. Therefore it is actually the sum for w, therefore each scalar will be equal to 0. As each scalar will be equal to 0, then by the definition of linearly independentness, the given set b is linearly independent, which implies curly b is linearly independent. Since for each bi is a basis for wi, then each scalar in the linear combination must be equal to 0, and it is a collection, and it is a sum of beta 1 plus beta 2 plus up to so on beta k, and each beta I belonging to its basis, as therefore it can be each beta I can be expressed as a linear combination of its basis bi, therefore and as bi is a basis, then each scalar in this multiplication must be equal to 0. Therefore this set curly b is linearly independent. Now it remains to prove that this curly b spans over space w. Okay, now second condition, we have to prove that curly b spans w. That is spans means if we take any element alpha belonging to w, then it can be expressed as a linear combination of its basis elements. Okay, let alpha belonging to W. As alpha belonging to W and W is nothing but W1 plus W2 plus up to Wk, then this alpha can be written as alpha 1 plus alpha 2 plus up to so on alpha k. Since W is nothing but W1 plus W2 plus up to so on plus Wk. Okay, now here alpha 1 is belonging to W1. Alpha 1 is belonging to W1 and curly V1 is the basis for W1. Then this alpha 1 can be expressed as a linear combination of its basis elements B1. Similarly, we can prove that for each alpha I can be expressed as a linear combination of elements of its basis. As also we know that Wi intersection Wj is equal to singleton 0 for each I not equal to j, and each alpha I can be expressed as a linear combination of elements of curvature, and which is true for each I running from 1 to k. Therefore, each alpha, it is true for each alpha 1, alpha 2 up to so on alpha k. Therefore, this alpha can be expressed as each alpha can be uniquely expressed as a linear combination of elements of curve uniquely, since each Wi intersection Wj will be equal to 0. Therefore, each alpha I can be uniquely expressed as a linear combination of its basis elements. Therefore, as each alpha can be uniquely expressed as a linear combination of elements of this curly V, then this curly V spans W, which implies curly V spans W. Now it remains to prove that dimension of this W is nothing but dimension of W1 plus dimension of W plus up to so on dimension of W. Here V is nothing but curly V1 plus curly V1 comma curly V2 up to so on curly V. Okay. Now and curly V is a basis for, which implies here as V spans W, which implies as V is linearly independent and it spans W, which implies curly V is basis for surface W. Okay, now dimension of this W is nothing but the number of elements in its basis, and number of elements in this basis are nothing but number of elements in basis B1 plus number of elements in basis B2 plus up to so on number of elements in basis Bk. Therefore, dimension of W is nothing but this B number of elements in this B1 plus number of elements in this B2 up to so on number of elements in this Bk, and number of elements in B1 are nothing but the dimension of W1. Number of elements in B2 is nothing but dimension of W2, since B2 is the basis for W2. Therefore, up to so on number of elements in this Bk is nothing but the base. Number of elements in this Bk is nothing but the dimension of Wk. Therefore, dimension of W is nothing but dimension of W1 plus dimension of W2 plus up to so on plus dimension of W, and hence the proof, which is the required result. Okay. Now the next theorem is, let P be a linear operator on finite dimensional vector space V, and let C1, C2, up to so Ck be distinct characteristic values, see, characteristic values of T and Wi be the characteristic spaces associated associated with the characteristic values Ci of linear operator T of T. That is, it is characteristic spaces are actually nothing but the null spaces. That is, Wi are the null spaces of T minus each eigenvalue. Okay, actually they are the null spaces of this operator T minus Ci of I. Then the following are equivalent. Here we have to prove that the following three statements are equivalent. Which first one is T is diagonalizable. Nullizable. Second one, the characteristic polynomial of T is given by f of x will be equal to x minus c1 to the power d1 into x minus c2 to the power d2 up to so on x minus ck to the power dk, and dimension of each wi is equal to di. Okay, and third one is dimension of w1 plus dimension of w2 plus to so on dimension of wk is equal to dimension of vector space. So here, given that P be a linear operator on a finite dimensional vector space V and C1, C2 up to so on Ck became distinct characteristic values of linear operator T, and Wi be the characteristic spaces associated with the characteristic value Ci of the linear operator T. As Wi are the characteristic spaces corresponds to characteristic value Ci is nothing but, actually its meaning is nothing but these Wi are the null spaces of linear operator T minus Ci. Okay. And then we have to prove that the following three statements are equivalent. That is, if T is diagonalizable, then we have to prove that the characteristic polynomial of a linear operator T has this form. That is, f of x is nothing but x minus c1 to the power t1, x minus into x minus c2 to the power d2 up to so on x minus ck to the power dk. And dimension of each wi is nothing but di. And dimension of w1 plus dimension of w2 plus up to so on dimension of wk will be equal to dimension of v. That is, we have to prove. As we have to prove that these three statements are equivalent, then if we prove 1 implies 2, 2 implies 3, and 3 implies 1, then the given result will be proved. That is, then from this we conclude that the given three statements are equivalent. First we have to prove that 1 implies 2, 2 implies 3, and if we prove 3 implies 1, then, then these three statements are equivalent to one another. Okay? Now, here, prove. Okay. Let given that P be a linear operator on a finite dimensional vector space V. Let P be a linear operator on finite dimensional vector space V, and C1, C2 up to so on Ck be distinct characteristic values of T. Distinct characteristic values of Okay. And WIs are nothing but the characteristic spaces associated with the characteristic value Ci of linear operator T. And we have to prove that the given three statements are equivalent. In order to prove these three statements are equivalent, here it is sufficient to prove that it is sufficient to prove that one implies two, two implies three, and 3 implies 1. That is implied and implied. Huh? Either we will prove 1 implies 2, 2 implies 3, and 3 implies 1, or 1 implied and implied by 2, 2 implied and implied by 3, and 3 implied and implied by 2. So first, prove. First, to prove that 1 implies 2. 1 is nothing but let T is a diagonalizable. Okay, diagonalizable. As T is diagonalizable, then from the definition of diagonalizable linear operator, any operator T is said to be a diagonalizable operator if there exists a basis curly B for V such that the matrix of linear operator T with respect to that curly basis curly B is a diagonal matrix. As given that T is a diagonalizable operator, which implies there exists an ordered basis curly B for linear for vector space V such that the matrix A of linear operator T with respect to ordered basis curly B is a diagonal matrix. Is diagonal matrix, which is from the definition of diagonalizable linear operator. And in previous lecture we proved that, and the diagonal entries, or diagonal entries of the matrix of this matrix A are the characteristic values of T, and each characteristic value is repeated certain number of times. Some number, okay, that is suppose let each Ci is repeated some Bi times. Okay. Then the matrix A has following block form representation. Block form representation. Okay, that is this A. This A is nothing but matrix of linear. This A is nothing but matrix of linear operator T with respect to ordered basis B, and which is nothing but C1 I1 0 0 so on 0, C2 I sorry here 0, C2 I2 0 so on 0. and so on. 0, 0, 0, so on. Ck I. And it is a square matrix of order n cross n, where each ij is a dj cross dj identity matrix. Since each ci is repeated, di times. Okay, and we know that now this is from given definition. Actually, we have proved this result in previous lecture. Okay, as given that t is diagonal as an operator, then it works all these things. Okay, now we know that the characteristic polynomial of linear operator t is given by determinant of xi minus t. That is nothing but the determinant of xi minus this matrix A, and which is nothing but, and we will denote characteristic polynomial by f of x. Okay. Now this determinant of xi minus t is nothing but, that is determinant of xi minus t is nothing but determinant of xi minus a, and which is nothing but xi is nothing but x into I1 0 up to so on 0 0 x into I2 up to so on 0 and so on 0 0 up to so on x into I2, and minus matrix A is nothing but C1 into I1 0 up to so on 0 0 C2 into I2 up to so on 0 0 0 0 0 and so on ck into I. Okay, now if we subtract, then we get, which is nothing but x minus c1 I 0 up to so on 0 0 x minus c2 I up to so on 0 and so on 0 0 x minus ck I, and it is a matrix of order m cross a. And now this determinant of, actually we have to take here determinant, not the matrix. Okay. So it is just determinant of m cross n. Now it's determinant, and determinant of diagonal matrix is nothing but the product of its diagonal entries, and which is nothing but, which is equal to x minus c1 to the power b. Actually, it is nothing but x minus c1 into I into x minus c2 into I2 up to so on x minus ck into I2. Now, each ij is a dj cross dj matrix. Therefore, each c1 is repeated. Sorry, each ci is repeated di times, and each and corresponding is identity matrix are given. Then, as each ci is repeated di times, then it is nothing but x minus c1 to the power d1 into x minus c2 to the power d2 up to so on x minus ck to the power dk. And which is nothing but the determinant of x minus t. Determinant of x minus t is nothing but the characteristic polynomial of a linear operator t, and characteristic polynomial of a linear operator t is denoted by f of x. Therefore, f of x is nothing but determinant of xi minus t, and which is nothing but x minus t1 to the power d1 into x minus t2 to the power d2 up to so on x minus ck to the power dk. So here half part of the second segment will be proved. Now we have to, now here we have to prove that dimension of wi is nothing but di. To prove that dimension of Wi is equal to dn. Then we have proved the second statement from 1. Okay. Now let dimension of Wi is nothing but something mi whenever I running from 1 to 8. If we take basis for this Wi, that is curly bi, then it is nothing but basis of the whole vector space V intersection its subspaces Wi whenever I running from 1 to k, which is from definition of basis. Now Bi is nothing but V intersection Wi. Then this curly Bi is subset of V and curly Bi is subset of this Wi. This V is a basis for vector space V, as it is a subset of this curly B, and curly B here, curly B is basis for V. As it is a basis, then this curly B is linearly independent, and every subset of linearly independent set is linearly independent. As here Bi is subset of B, which implies curly Bi is a linearly independent subset of V. And here this Bi is subset of Wi, then this dimension of Bi is less equal by dimension of Wi, and dimension of Wi we consider mi. Therefore dimension of this curly Bi is less equal by this mi. Actually, dimension of basis is not given if number of elements in basis are nothing but the dimension of its corresponding subspaces. Before that, let us consider. Let ni be the number of elements in curly Bi whenever I running from 1 to k. But for particular, if we take for Bi, then Bi contains ni elements. Therefore, this ni is always less equal by dimension of Wi, since each Bi is a subset of Wi, which implies, but the dimension of Wi is nothing but mi. Therefore, ni is always less equal by mi whenever I running from 1 to k. Let us take this one as equation 1. Okay, now as we know that W1, W2 up to so on Wk be the characteristic spaces associated with the characteristic values Ci of linear operator T, and each Ci is, that is C1, C2 up to so on Ck be distinct characteristic values of a linear operator T. Therefore, each Wi contains at least one characteristic vector. Therefore, dimension of this Wi is greater or equal by 1. Okay. So 1 is less equal by dimension of Wi. That is dimension of Wi is greater or equal by 1, since the Wi are the characteristic spaces associated with the characteristic values Ci of linear operator T. Therefore, dimension of Wi is at least 1. Okay. And dimension of Wi is less equal by Di, since Di's are nothing but the, that is Ci's are nothing but the, each Ci is repeated Di times, then dimension of Wi is at most Di. Now, which implies 1 is less equal by dimension of Wi. Dimension of Wi is nothing but mi. Mi is less equal by Di. So, which implies mi is less equal by Di. Therefore, from equation 1 and 2, ni is less equal by mi is less equal by Di, which implies from 1 and 2, from 1 and 2, we get ni is less equal by mi is less equal by Di. Now, taking the summation from I from 1 to k, we get summation I from 1 to k ni, which is less equal by summation I from 1 to k mi, and which is less equal by summation I from 1 to k Di. Okay. Now here This ni is nothing but number of elements in curly bi, and I is running from 1 to k, and number of elements in here given that V be a finite dimensional vector space. Let us suppose dimension of this V is nothing but something n. That is, first consider here, suppose something consider dimension of V is suppose something n. Since V is a n dimension, sorry, finite dimensional vector space, then we can consider suppose its dimension will be equal to n. So each Ni is nothing but the number of elements in each basis Bi, which is for each I running from 1 to k. And in previous theorem we have proved that dimension of vector space, sorry, dimension of B is nothing, dimension of W is nothing but the number of elements in B1 plus number of elements in B2 plus up to so on number of elements in Bk. Therefore, as ni be the number of elements in each bi, then n1 plus n2 plus up to so on plus nk is nothing but dimension of its w, that is here dimension of this v, and which is nothing but n. Okay, whenever summation I running from 1 to k, ni, that is n1 plus n2 plus up to so on nk, then which is nothing but dimension of w1 plus dimension of w2 plus up to so on dimension of wk, and which is nothing but dimension of your vector space v, and which is nothing but the n, that is which is the number of elements in basis b, and number of elements in basis b is nothing but the dimension of vector space v, and which is n. Okay, therefore n is less equal to summation I running from 1 to k mi. Now here d1 d2 up to so on dk are nothing but the, that is each ci is repeated di times. Therefore, and we know that fx equal to x minus c1 to the power d1 plus x minus c2 to the power d2 up to so on x minus ck to the power dk, and d1 plus d2 plus up to so on dk is nothing but the degree of a polynomial f of x, and which is also nothing but n. So which is nothing but n. Since d1 plus d2 plus up to so on dk will be equal to n, therefore summation I running from 1 to k mi is lying between n to n. Then which implies summation I running from 1 to k mi must be equal to n. But n is nothing but summation I running from 1 to k mi is equal to summation I running from 1 to k di. Okay, which implies summation I running from 1 to k di minus mi is equal to 0. Now here mi is less equal by di, as mi is less equal by di, which implies di minus mi is greater equal by 0, which is from which mi is less equal by di. But this sum is equal to 0, and di minus mi will be greater equal, di minus mi is greater equal by 0, which implies this di minus mi must be equal to 0, which implies di minus mi must be equal to 0, which implies di is equal to mi. But we consider this mi is nothing but the dimension of each wi, which implies dimension of wi is equal to di. So here we have proved 1 implies 2. Now we have to prove that 2 implies 3. Okay. Second, to prove that 2 implies 2 is nothing but, so let the characteristic polynomial of p is fx is equal to x minus c1 to the power d1 up to so on x minus ck to the power dk, and dimension of wi is equal to di. And here we have to prove that dimension of w1 plus dimension of w2 plus up to so on plus dimension of wk is nothing but the dimension of vector space V. Okay, now the characteristic polynomial is f of x equal to x minus c1 to the power d1 into x minus c2 to the power d2 up to so on x minus ck to the power dk. Okay, now degree of f of x is nothing but. Here, each Ci is repeated di time. Therefore, degree of f of x is nothing but this d1 plus d2 plus up to so on dk. That is degree of this polynomial. And degree of this polynomial is nothing but summation of these terms. That is d1 plus d2 plus up to so on dk. That is degree of x minus c1 to the power d1 up to so on degree of x minus ck to the power dk. And degree of this polynomial is nothing but d1, which is nothing but d1 plus d2 plus up to so on plus dk. But from this, dimension of wi will be equal to di. Then d1 is nothing but dimension of w1. D2 is nothing but dimension of W2. Therefore, up to so on, dk is nothing but dimension of Wk, which implies degree of f of x is equal to dimension of W1 plus dimension of W2 plus up to so on plus dimension of Wk. But degree of polynomial f of x is nothing but n. Since d1 plus d2 plus up to so on dk is nothing but n. Since dimension of u will be equal to n, which implies n equal to dimension of w1 plus dimension of w2 plus up to so on dimension of wk. But we know that this n is nothing but dimension of a vector space v equal to dimension of w1 plus dimension of w2 plus up to so on dimension of w2. So here we have proved that 2 implies 3. Now it remains to prove that 3 implies 1. Okay. To prove that 3 implies 1. That is, here we have to take dimension of this v is nothing but dimension of w1 plus dimension of w2 plus up to so on plus dimension of wk. And we have to prove that P is diagonal. Okay. Now from previous theorem, let W will be equal to W1 plus W2 plus up to so on plus W2, which is a subspace of vector space V. Okay. Now where each Wi is a characteristic space associated with characteristic value Cn. Now from previous theorem, previous theorem, if W will be equal to W1 plus W2 plus up to so on Wk, and Wi's are the characteristic spaces associated with the characteristic value Ci, then this dimension of W is nothing but dimension of W1 plus dimension of W2 plus up to so on dimension of Wk. But dimension of W1 plus dimension of W2 plus dimension of Wk is nothing but the dimension of V, which is equal to dimension of V. So here that W is a subspace of V and dimension of W will be equal to dimension of V. Then it is possible if and only if W and V are same. Since as W be any subspace of a vector space V, then there are 3 possibilities. Either W is a zero subspace, or W will be equal to 0, or W is any proper subspace of V. But given that dimension of W will be equal to dimension of V, then W is not a zero subspace and W is not a proper subspace of V. If it is a proper subspace, then its dimension must be less than dimension of V. But here as dimension of W will be equal to dimension of V, then W is nothing but V itself, which implies W is equal to V. But W is nothing but W1 plus W2 plus up to so on Wk, and W will be equal to V, which implies V is nothing but W1 plus W2 plus up to so on Wk, and Wi are nothing but the characteristic spaces associated with the characteristic values Ci, and curly Bi here, curly Bi are the basis for, or are the basis for ordered basis for Wi containing characteristic vectors. Okay, therefore curly b equal to curly b1 comma curly b2 up to so on. Curly bk is an ordered basis is an which is from previous theorem. Ordered basis for w, but here w is nothing but v, for v containing characteristics containing characteristic vectors. Since this curly b1, curly b2 up to so on curly bk are the characters, are the basis for the spaces w1, w2 up to so on wk, and this w1, w2 up to so on wk are the characteristic spaces associated with the characteristic values ci, and characteristic spaces are nothing but the collection of characteristic vectors. Therefore, this beta 1, beta 2 up to so on beta k must be it contains characteristic vectors. Okay, containing characteristic vectors. Then by definition of diagonalizable operator, any operator T on a finite dimensional vector space V is said to be a diagonalizable operator if there exists a basis curly B for linear or for vector space V such that its every element is a characteristic vector. As here curly B is a basis and this B1, B2 up to so on curly Bk are the collection of characteristic vectors. Then by the definition of diagonalizable operator we say that T is a diagonalizable operator, as T is a diagonalizable operator which implies 3 is implied by 1. So here we have proved that 1 implies 2, 2 implies 3 and 3 implies 1, which implies that the 3 statements are equivalent and hence the okay. Thank you for watching the lecture.